Welcome to the first lecture of this week. So my name is Umut Orguner, and you might have seen me in the first lecture. So I will be teaching you the second part of EE501. So let me write my name here. My email address is umut@metu.edu.tr. Okay, so you can reach me from this address anytime you like. So I will start this lecture first by making a brief review of what you have learned so far about projection theorem. You have seen that if we have a linear space V, and suppose that we have a subspace of it, M, then you can always write this overall space as the orthogonal direct sum of two subspaces, M and M perp. So this is the perp sign, so it means the orthogonal complement, and this is an orthogonal direct sum decomposition. Remember, the proof of projection theorem is actually based on just this fact. So such a fact means three things at the same time. And it means, the first thing it means the following. First, I have the V is the sum of M and M orthogonal complement. Okay? What does this mean? This fact means that I can write any V inside capital V as the sum of two vectors, V1 and V2. All right? And here, V1 is in M, and V2 is in M orthogonal complement. This is what this summation means. It is the summation of subspaces. So any vector in V can be written as a sum of two. This is what the summation means. Sum of two vectors, V1 and V2, and V1 is coming from M, and V2 is coming from M orthogonal complement. So remember, then on top of this summation sign, we have a circle, and that means the direct sum. Okay, so if I add the direct sum notation on top of this summation, that is going to mean a very important thing, and it tells us that in this decomposition, I am decomposing V into V1 and V2. In this decomposition, the decomposed components are unique. So V1 and V2 are unique. Okay, and the only thing that brings this is the direct sum decomposition property. It means that the subspaces M and M orthogonal are actually linearly independent. Okay, and from that linear independence, you can show that when I decompose any V in this form, then this decomposition is going to be just unique. Okay, and the third thing about this one is this orthogonal sign. All right, is the perp sign, and when I write this thing like this with the additional orthogonal sign, then it again means something very important about this V1 and V2. Since V1 is in M and V2 is in M orthogonal complement, these two vectors should be orthogonal to each other. And that is coming from the orthogonal sign. So a single statement, V is M orthogonal direct sum, M orthogonal complement, it means that these three facts are actually correct. And remember, the projection theorem actually is based on this fact. And if I take any V in capital V, then when I try to project this V onto the subspace M, then we know that the answer is going to be just V1. The component of this vector, the unique component of this vector inside M. Okay? Similarly, if I want to project, this is the orthogonal projection, of course, project onto M orthogonal complement V, this is going to be V2. How can I check that the first fact is actually true? So what I can do is that I can actually subtract the projection from V, then I get V minus V1, and we know that this is V2. And I know that V2 is an M orthogonal complement, so this is orthogonal to M. this subtraction is orthogonal to M. Okay, that is the orthogonality principle in the projection theorem. Similarly, in this case, V minus V2, in this case, V minus V2 is V1, and this is orthogonal to M orthogonal complement. If something is orthogonal to M orthogonal complement, it is going to be in M, and this is V1. All right? So I will, before I continue with the other facts, I'm going to ask you a question. So suppose that V is equal to R2, okay? I have the two-dimensional vector space, and suppose that I have decomposed V into an orthogonal direct sum decomposition. M orthogonal direct sum, M orthogonal complement. Here orthogonality will not be important actually, but still let us say that this is an orthogonal direct sum decomposition. Then I will ask you the following. Suppose that V, I have a vector V which is not inside M. Okay? I have V, the vector V, which is not in the subspace M. Then can I say, there is a question mark, V is going to be inside M orthogonal complement? Okay? So do you think I can make such a claim? This is a direct sum decomposition. So when one of the vector, when a single vector is not in M, can I say that it is going to be inside M orthogonal complement in the other space? In this case, the answer is no. And this is because sometimes students have a different visualization for this direct sum decomposition. So a direct sum decomposition is not something like this. Suppose that this is my V, okay? A direct sum decomposition is not really dividing this space into two parts, okay? This is M, and this is M orthogonal complement. Such a visualization is not really correct. All right? I will give a very simple example. So I know that R2 is x-axis and y-axis. Okay? Or I can write, instead of this, I can write span of 1, 0. This is my x-axis subspace. This is my M. And the y-axis is span of 0, 1. Okay? And this is my M orthogonal complement. You see that this vector is always orthogonal to that vector, etc. Okay? So now what am I doing? I am doing here, this is my R2, and I am writing a direct sum decomposition. Span of 1, 0 are vectors in this form. So it is this subspace here I'm talking about. Vectors whose tip lie on the x-axis is my first subspace. And the second subspace is the y-axis. Vectors whose tip lie on the y-axis. This is the second subspace. Okay? And I know that R2 is a direct sum of these two subspaces. Actually, it is orthogonal direct sum. All right? So now I can ask you the following equivalent question. Suppose that I have a vector which is not on the x-axis. Okay? This is my first subspace. Suppose that I have a vector which is not on this subspace, x-axis subspace. That vector, should that vector be inside the y subspace always? That is the question. You see why it's meaningless here. Because I can easily have a vector which is looking like this. And that means that, suppose that I have vector 2, 3, okay? I know that this is not inside M. This is not on the x-axis. And this is not on the y-axis either. Okay? But here you see that I can write V as 2, 0 plus 0, 3. This vector is in M, and this vector is in M orthogonal complement. Okay? So that is the meaning of this direct sum decomposition. These subspaces are actually like coordinates. Okay? So I can write any vector using the coordinates in M and the coordinates in M orthogonal complement. So in this example, x-axis is my first subspace and y-axis is my second subspace, and I can write any vector as the sum of two vectors, one on the x-axis and one on the y-axis. But when I have a single vector, that vector really does not have to be in either of M or M orthogonal complement. So this actually shows that this decomposition is not looking like this. We are not dividing a subspace into two disjoint subspaces. We are not dividing the overall space into two disjoint subspaces. Instead, we are writing this whole R2 subspace as the sum of two subspaces. And that means that I can write any vector in this linear space as the sum of two vectors. The first one coming from the first subspace and the second one is coming from the second subspace. And this decomposition is unique. That is what this circle sign is telling me. And when I have the vector 2, 3, I cannot find any other decomposition which looks like this. Okay? And furthermore, these two vectors are orthogonal to each other, and that is what this orthogonal sign is meaning. Okay? So I want you to remember that when we make such a decomposition and when we decompose V into two vectors, these two vectors that we find in our decomposition are nothing but the orthogonal projections of this vector V onto the subspace M and subspace M orthogonal complement. That is going to be important in the later parts of the course. So then you have seen the application of the projection theorem. I won't write the projection theorem here. We know that the projection theorem holds, but you have seen some applications of the projection theorem onto the general spaces. If I have a linear space, let us say, if I have an overall space V, and when I have a subspace of it, span of V1, V2, going until Vk, a k-dimensional subspace, suppose that this is n-dimensional, then you have learned how to find the projection of any vector V onto this M. Okay? So you have learned how to find such a projection. And in that case, we have to use the principle of orthogonality. Okay? So I know that I can write my projection, which is going to be inside M, as a linear combination of these basis vectors. Alpha 1 V1 plus alpha 2 V2, going until alpha k Vk. And then you can actually subtract this projection from the original vector V minus M has to be orthogonal to the subspace M. Okay? And being orthogonal to the subspace M means that this V minus M should be orthogonal to V1, then V2, then going until Vk here. Okay? And when you substitute this M into here, and when you obtain the equations that you get from this, you can solve for alpha. So here, unfortunately, the battery of my microphone is running out, so I'm going to change it, and then we'll come back. Okay, now I'm back. So here, let us look at this again. So I have V minus M, and this should be orthogonal to this k k basis vectors, v1 to vk. Okay, and I know that I have k unknowns here, alpha 1, alpha 2, alpha k, and then I get k linearly independent equations, and then I can solve them for the optimal alpha that would give me my orthogonal projection. And finally, you have seen the application of projection theorem onto Cn. Okay? In Cn, these are now not in a function space, but they are usual vectors. Okay? And in that case, you might have called this as span of, let us say, m1, m2 going until mk, and now these are vectors mi in Cn. Okay? And when these vectors are the basis vectors of our subspace, then I can actually fill in these basis vectors into a matrix to form the matrix B, m1 and 2, going until mk. Okay? This is, in that case, an n by k matrix. All right? And then you have calculated a projection matrix. Suppose that you want to find the projection of any vector x, or let us say v, it really doesn't matter, v onto this subspace M. Okay? You have seen that you can actually do this by multiplying this vector v with a matrix. Okay? PM. And you have found the formula for this PM using this type of idea there, and the formula was just this: B Hermitian B inverse B Hermitian B. I have a slight change of notation here than your other instructor's notation. Probably the other instructor is using this B star here. B star is the same thing as B Hermitian in my notation. Hermitian means transpose and complex conjugate together, and in my notation, B Hermitian is the same thing as B star. Okay? Remember this matrix B Hermitian B. It is called as the Gramian matrix. Okay? Gramian is coming from the mathematician Gram. So you learned about Gram-Schmidt orthogonalization. It's the same mathematician here. This matrix is named after his name. And B Hermitian B is the Gramian matrix. Remember, if you try to calculate it here in the general case, then you have seen the inner products, a matrix composed of cross inner products of these basis vectors. And this B Hermitian B, the Gramian matrix, is invertible if and only if the vectors, the columns of B, are linearly independent. Okay? B Hermitian B is invertible. So this formula is valid if and only if, and this is IFF, it means if and only if. I can sometimes write just this thing. It is the same thing, double-sided implication. If and only if columns of B are all linearly independent. We are going to see that this means actually that B is full column rank. That is the name, or that is the qualifier given to B having linearly independent columns. When I say that B is full column rank, or B has full column rank, then it's going to mean that all columns of B are linearly independent, and B Hermitian B in that case is an invertible matrix. So this formula is only valid when the columns of B are linearly independent, when these vectors are actually linearly independent with each other. But then what can I do when these vectors are not linearly independent? So suppose that M is given like this. So span of, let me say, M1 and M2. Or let me increase the vectors, mk. And suppose that one of the vectors here is linearly independent with the other vectors. Okay? Suppose that one of the vectors, let us say mk is linearly independent with the earlier ones, okay? Then this means that my adding this vector into this span does not bring any new information. That means that I can remove this one from this span. So this is the same span as mk minus 1, okay? If one of the vectors is linearly independent, is not linearly independent with the others, then I can remove it and this span will be exactly equal to the original span, okay? And suppose that when I remove this one, then all vectors are linearly independent. Then I'm going to form my B vector out of those linearly independent vectors, m1 to mk minus 1, as the columns, okay? Then this matrix is going to be, Gramian matrix is going to be linearly, is going to be invertible. So here, if one of the vectors is linearly dependent with the other ones, and if you try to form the original Gramian matrix by forming your B like that, everything is going to be wrong because your Gramian matrix is no longer going to be invertible. Okay? So this formula is going to be a completely wrong formula in that case. So if you have linearly dependent vectors, you need to remove linearly dependent ones from the set until you have a basis set here. Okay? We know that in the basis set we need to have linearly independent vectors. All right? So you need to remove linearly dependent ones until you get a set which is linearly independent, in which all vectors are linearly independent. And since these spans are actually the same, and if m1 to mk minus 1 are linearly independent, then this is going to be a basis vector, okay? This is going to be a basis set for this subspace. And then you can form your B out of the basis vectors, okay? So if you start with a set which is not a basis set, then if you try to form your B matrix like this, you are not going to be able to invert that Gramian matrix, which is going to be a catastrophe. All right? So you have to reduce the number of vectors until you get a basis set, and then you can form your B matrix from the basis vectors, and then you can invert the Gramian, surely. So this completes my review for the earlier parts of the course. I didn't go far back here at all. So I have only reviewed the parts that are going to be useful for me. And now we're going to start with the last application of the projection theorem, which is going to be the application of the projection theorem onto solutions of linear equations. Projection theorem onto solutions of linear equations. So now let us start with the new subject. So in this case, I will have the equation AX equals to B. Okay? We would like to solve this equation for x, and here A is going to be in C m by n. A is going to be a known m by n matrix, and B is going to be in Cm, and x is going to be in Cn. Okay? Here A is known, B is known, and x is unknown. Okay? We would like to solve this equation for x. So this type of equations appear in many parts of electrical engineering, and actually in many parts of the different studies of engineering. For example, if you are working on fluid mechanics or computational fluid dynamics, you always solve this type of equations, but with millions of variables, okay? And if you are working on computational electromagnetics, you are again solving this type of equations with really a lot of different variables in X. So when you have an A matrix with millions of variables, or when you have an X vector with millions of variables, the solution of such an equation would be really problematic. Of course, in this course, we're only going to be seeing some basic parts of this theory, and we're going to skip the so-called iterative solutions for this type of equations. Actually, there are courses specifically given for the iterative solutions of such large equation systems with millions of variables, and in the case when A is a sparse matrix, for example. So in this course, we're only going to be concentrating two problems. So I'm going to ask two questions to you about this equation, and we're going to give the answers to these questions first, and then we're going to be working when the answers are no. Actually, we're going to see how to overcome the problems that we encounter on the process. The first question is going to be the following: is there a solution? Is there an exact solution? This is my first question. So, can I find an exact solution to this equation? Or what is the condition for me to be able to find an exact solution to this equation? And the second question is going to be the following: when there is a solution, when there is an exact solution, is the solution unique? Okay, that is our second question. So we are going to see that both questions have very neat answers mathematically. So we are going to see that the answer of the first question is related to the range space of the matrix A and the B vector. And we are going to see that the answer of the second question is going to be related to the null space of the matrix A. All right? So now I'm going to start illustrating you the theory on some toy examples. So when I ask these questions in a real classroom, I usually get the following answer from the students. Is there an exact solution, I ask? And the answer is usually, if A is invertible, yes. So that type of answer means that the corresponding student does not really know the theory. So the first thing that we have to be making sure here is that M is not equal to N in general. Okay? This means that A really does not have to be a square matrix. Okay? Invertibility is only defined for a square matrix. So you cannot really talk about the invertibility of a rectangular matrix when M is not equal to N. Okay? So therefore, when we teach this theory, we really do not talk about invertibility initially, because A really does not have to be a square matrix for which invertibility is defined. For a rectangular matrix, invertibility is undefined, and saying that A is invertible or not invertible really does not make any sense. So here I'm going to be starting with some toy examples. So let me start with the following. So the first example is really simple. So I have the following A matrix. This is my A times X is equal to 2 and 2. Okay? So this is my B vector. And X is in this case is just an element of C. Or you can say in this case just R, a real number, since both A and B are real. Okay? So in this case, do we have any solution? We have to answer this question. And when we have, or if we have a solution, then, is that solution unique or not? Or is there multiple solutions for the equation here? All right. So I will first be asking the following question: what is the range space of A and what is the null space of A. Okay? I will first define these concepts. Of course, you know them by now from the earlier material in this course and from the linear algebra course that you have seen in your undergraduate studies. But here, let me write what the definitions were. So, range space of A is Y inside the codomain of the linear transformation. Let me say this is my matrix A. It's a transformation from a space to another space. Okay? And matrix A just transforms X's into B's. Okay? B's are in Cm. Therefore, the codomain of the transformation is Cm. And the domain of the transformation is Cn. All right? This is the domain. And this is the codomain. Or sometimes people call this the range of the transformation. Okay? It is the same thing. So range space of A is a subspace which is composed of elements inside the codomain, okay, in Cm, such that there exists X in Cn, the domain satisfying Ax equals to Y. Okay, let me erase this thing and write it here. So range space of A is the set of vectors inside the codomain such that there exists X in the domain which would be transformed into Y. Okay? So range space of A is a subspace of the codomain. All right? And null space of A are the elements of the domain such that A times X is equal to 0. Okay? And the null space of A is a subspace of the domain. Okay? So I have null space of A. And now let us look at these subspaces. So in range space of A, for a vector to be inside range space of A, there has to be a vector in the domain which is transformed by A onto that vector. Any vector which in the codomain which can be obtained by transforming any vector in the codomain by A is inside the range space. Any vector which can be obtained by a transformation of a vector in the domain by A is in the range space. Okay? And null space condition is that any vector which is transformed by A to the 0 vector, suppose that this is my 0 vector inside the codomain, then all vectors inside the null space should be transformed onto the 0 vector. Okay? These are the definitions of range space and the null space. So here I'm going to be actually coming up with another description of the range space. So if a vector Y is inside the range space, then I can write that vector as A times X for some X value. Okay? Let me write the columns of A, A1, A2, going until, let me say, AN here. And X is given by these coefficients, X1, X2, Xn. Then this has to be equal to Y for a Y to be inside range space. Okay? So now and these are my column vectors. Okay? These are the column vectors of A. And this is the condition for any Y to be inside the range space. Now these are scalars, and by the rules of matrix vector calculation, this matrix times this vector is the following. Y is equal to x1 times a1 plus x2 times a2 going until xn times an. Okay? So for a vector y to be inside the range space, then we need to have that vector y, we need to be able to write it as a linear combination of the columns of A. Okay? For a vector y to be in the range space, I need to be able to write that y as a linear combination of the columns of A, where the coefficients are nothing but the elements of x vector here. I'm saying that such an x vector exists. All right? So that is why the range space is nothing but the column space of the matrix. Okay? The span of the columns of the matrix is the range space. And what about the null space? These are the vectors which when multiplied with A would give us just a zero vector. And remember, we have the so-called rank nullity theorem. Dimension of range space of A plus dimension of null space of A is equal to the dimension of the domain of the linear transformation. Okay? And here, what is the domain? V is my domain here, and its dimension is n because it is Cn. As a result, the rank nullity theorem for matrices is nothing but dimension of range space of A plus dimension of null space of A is equal to n, the number of columns. Number of columns. Okay? And the dimensions of range space of A and the null space of A should satisfy just this equation. All right? If the range space dimension is 1, which means that we have only a single linearly independent column, in that case the dimension of the null space should be number of columns minus 1. Okay? So here I will erase my questions, and we will come back to the questions over and over. So now let me look at this A matrix. A is given as 1, 1, and B is here 2, 2. Obviously, you see that the solution is really very easy in this case. But really, what I want to do here to interpret this equation in an abstract way by making relationships between range space of A and this vector B and null space of A and the uniqueness of this transformation. Okay? Uniqueness of the solution here. So here, what is range space of A? We know that range space is the span of the columns of the matrix. It's the column space of the matrix. So I have span of 1, 1. It's only a single column. So this is my range space of A. And what is the dimension in this case? There is only one linearly independent vector in the basis. Therefore, dimension of range space of A is equal to 1. Okay? So what should be the dimension of the null space? In this case, the number of columns is 1. Dimension of the range space is 1. Dimension of the null space should be equal to 0. But we can see it directly from the A itself as well. So which axis would satisfy this equation? This is the equation A times x is equal to 0. Okay? Which axis, which real numbers would satisfy this equation? And we know that it is only the 0 which is satisfying this equation. As a result here, I can say that null space of A, you can write it, is only composed of 0. All right? Or you can say dimension of the null space of A is equal to just 0. It's a zero-dimensional subspace because there is no linearly independent vector in its basis set. Okay? This is a zero-dimensional subspace, is the null space. Okay? Now I'm asking you the following question. Is there a solution to this equation? And you obviously see that there is a solution, and that solution is x is equal to 2. Okay? That is my solution to this equation. And since I have found an exact solution, then I will ask you, is this solution unique? and try to look for another x value other than 2 which would satisfy this equation. And you see that you won't be able to find it. Okay? And as a result, we have there exists an exact solution. This sign is there exists an exact solution. And this solution is unique. Okay? Now I will just change the example to a little bit more problematic one. And that example is going to be the following. The A matrix is going to be remaining the same. And I have x is equal to 2, 1. All right? So now we have the same range space and the same null space. And if I ask you the same questions, again, is there an exact solution? And you see obviously that there is no exact solution. I cannot find any single x value which would satisfy this equation. Okay? And then when we don't have any solutions, any exact solutions, we cannot talk about uniqueness either. Okay? So in this case, I have no exact solution. And then I can talk about the uniqueness. So now what is the difference between these two examples in terms of the B vector A matrix? Okay? Range space of A was the same, null space of A was the same, only B changed here from this example to that one. Okay? And we saw that when in this example we have, while in this example we have an exact solution, in the second one we don't have an exact solution. Okay? This is related to the vector B. And the existence of a solution, existence of an exact solution is related to whether B is an element of the range space of A or not. Okay? So in the first example, B is 2, 2. Do you think it is inside the range space? I know that if I have a linear space, which is a one-dimensional linear space, and any vector in this space can be written as a scalar multiple of this 1, 1. Let us say alpha 1, 1. Okay? And we see that this B vector is inside the range space of A for the first example. Okay? That means that there exists an X such that this B vector can be written as the linear combination of the columns of this matrix. And there is only a single column. Therefore, this means that there exists a scalar here, which when it multiplies the column of this matrix, I would obtain this 2, 2. This just means that in linear algebraic terms, this means that this B vector is inside the range space of this matrix A. Okay? And when B is inside range space of A, then we can surely say that there exists an exact solution. Okay? There exists an exact solution. What about the uniqueness? We will come to that later. But let us investigate this second equation. In this case, this is my B, and this is our A. In this case, can I say that B is inside range space of A? This 2, 1 vector, can I write it as a linear combination of the columns of A? And the answer is obviously no. Any linear combination of this single column would have equal elements, alpha and alpha. Okay? And in this case, this vector, since its elements are not equal to each other, is simply not in range space of A. That is why there exists no exact solution in this case. Okay? So we have this interesting fact. In mathematical terms, existence of a solution to a linear equation in the form Ax equals to B is related to range space of A and the vector B. If B is inside the range space of A, then there exists at least one exact solution, and if B is not in range space of A, then there doesn't exist any exact solution. Okay? So now I will look at a third example. All right? The third example is going to be as follows. The example is given like this. So now you see that this A changed its size. I have no longer A with one column only. I have A with two columns. And now let us concentrate on this A. And I have this B. So now let us look at the range space of A. Range space of A is span of the columns 1, 1, and 2, 2. Range space is the column space. Span of the columns is span of 1, 1, and 2, 2. But you see that 2, 2 is linearly dependent with 1, 1. The second column is linearly dependent with 1, 1. As a result, I can only write span of 1, 1 here. I can remove the linearly dependent vector and I get a basis vector for the range space of A here. If I put here also the vector 2, 2, then the set, it would be correct still, but the set I write here would not be a basis vector. Okay? Always try to write a basis vector here with span. So now, what is the dimension of range space of A? In this case, it is again 1 because we have only a single basis vector, single linearly independent basis vector. And here, I can go into the null space, but just before the null space, let me ask the following question. Is B, this vector, is B inside range space of A? Yes, it's similar to the first example here. This is the range space of this matrix and this matrix are the same, and therefore this B vector is inside the range space of this matrix as well. So here, there exists an exact solution. Can you find me such an exact solution? In this case, you have to remember that X is two-dimensional, okay? This is X1 and X2, which means that my domain has increased its dimension. In the earlier examples, I had one-dimensional domains because X was a real number. But in this case, X is a vector, so I have R2 or C2 as my domain, and as a result, here, we have the X that you give me should have two elements. I can, for example, find an exact solution like this, 2, 0. When I multiply this X with this matrix, I get 2, 2. Or I can find another solution, just here, 0, 0, 1. This is just another solution, okay, to the same equation. All right? Or I can write X equals to, let me say, 1 and 1 over 2. This is also an exact solution to this equation. So then, what actually makes this example? In the first example, I had a unique exact solution, but in this new example, I really do not have an exact solution. And actually, you can see that you can construct infinitely many exact solutions for this example. Okay? So now what changed? Definitely the range space did not change. I have the same range space. Okay? Then I'm going to be asking, what about the null space? Okay? So in the earlier example, I had null space of A which is a zero-dimensional subspace, which was composed of only the zero vector or zero number here, okay? And let us look at the null space for this example. So the first question that I'm going to be asking, what is the dimension of the null space? We need to apply here the rank nullity theorem. What is the dimension of the domain of this matrix? Domain is R2. For this matrix, the domain is R2, or let me say C2, and codomain is again C2. Okay? In the earlier case, the domain was C. This is only a scalar, okay? And codomain or range was C2. Okay? This matrix took scalars and it turned them into vectors with two elements. This matrix takes two vectors with two elements and it converts them into vectors with two elements. Okay? Therefore, domain is C2 for this matrix and codomain is C2. So what is the dimension of the domain? It is 2 here, and dimension of range space of A plus dimension of null space of A should be the dimension of the domain, or the number of columns of the matrix, which is 2 here. Okay? Dimension of the range space is 1. As a result, dimension of the null space of this matrix should be 1 as well. All right? So dimension of null space of A for this matrix is just 1. That means that the null space of A of this matrix is going to be span of only a single non-zero vector. In the basis vector, in the basis set, I will have only one linearly independent vector. Okay? So, as a result, for me to be able to find the basis set for the null space, it is sufficient that I find only a single non-zero vector, x, which when I multiply it with A, would give me 0, 0. Okay? So I need to solve this equation for a single non-zero vector, x1, x2, 1, 1, 2, 2, and 0, 0. That is the equation for the null space. All right? And you see that if I choose x1 equals to 2 and x2 is equal to minus 1, then I would get 2 and minus 1. Here, then I would get the null space. Obviously, you can find infinitely many such vectors. Span of 2, 1 is equal to span of 1 and minus 1 over 2. Okay? You can write it like this. There is no difference. Okay? But this is my null space in this case. So you see that in the first example and this new third example, the null spaces are different. In the first example, the null space was composed of only 0 vectors. And in this third example, and the null space was 0-dimensional, and in this third example, the null space is 1-dimensional. Okay? It has one linearly independent basis vector. All right? So therefore, this should be the main difference about the uniqueness of this case and non-uniqueness of this case. Now I want to show you something. I have actually found 2 different solutions. Let me say this is my XA, and let us say this is XB, and let us say this is XC. I know that all 3 of these solutions are exact solutions of this equation for this equation. XA, XP, XC are all exact solutions. Okay? Let me subtract XA from XP. XP minus XA is 0, 1 minus 2, 0. Okay? And this gives me minus 2 and 1. So now I will ask you whether that difference vector, is it inside the null space of A? Null space of A is the span of this single vector. And you see that if I multiply this vector with minus 1, I get that difference. Okay? So this difference is actually inside null space of A for this example. Okay? So here I will try another thing. Subtract xc from xp. So I have this one. 0, 1 again. Minus, I have 1 and 1 over 2. Okay? Then it gives me minus 1 and 1 over 2 here. So do you think this new difference vector, is it inside null space of A? The answer is yes. If I multiply this basis vector with minus 1, I get again that one. So what is important here is that whatever solution I find here, whatever exact solution I find, when I subtract those solutions from each other, I will always get a vector inside null space of A. Okay? So this is very, very interesting. However many solutions I find, when I subtract those solutions from each other, you can do other subtractions, xa minus xc, etc. Okay? So but you will always see that the vector that you get as a difference vector will be inside this null space of A. Okay? This tells us something very, very important. Okay? So I'm running out of space here. So let me write here. Sorry, my board use was really bad in this lecture. So suppose that you have the equation AX equals to B. Okay? Suppose that you find a single solution. Suppose that you find a single exact solution to this equation. Okay? I will call that exact solution as XE. Okay? And this is an exact solution. Suppose that I have also a null space of A, and suppose that I find a vector M inside null space of A. Okay? Now I am going to add that vector M into my exact solution. So I will write XE plus M. Do you think such a vector, XE is an exact solution, do you think XE plus M, do you think it can be also an exact solution to the same equation AX equals to B? In order to be able to understand that, I'm going to multiply this candidate solution with A, and I will check if A times XE plus M is equal to B or not. Okay? Let us do that. A times XE plus M is equal to, I want this to be B, for this to be an exact solution. A times XE, but A times XE is B, because XE is an exact solution, and plus A times M. But M is inside the null space, okay? So A times M is equal to 0. But this is equal to B, okay? So we see here that when I have an exact solution, if I find an M inside the null space of A, and if I add that M vector into my exact solution, I would get another exact solution. XC plus M is also an exact solution. Okay? So when we have exact solutions, when we add the elements of null space of A to those solutions, we get new exact solutions. And suppose that I want uniqueness, okay? Suppose that I really do not want any multiple solutions, okay? I want only one and only one solution. In that case, what should be the condition for this uniqueness? I know that if inside null space of A, if there exists a non-zero vector inside the null space of A, my solution will never be unique. Okay? Because in that case, I can find a non-zero M, and I can add it to my exact solution, And then I would get another exact solution which is different than my original exact solution. So if inside null space of A there exist non-zero vectors, then my solution will never be unique. Any exact solution will not be unique. But if in my null space there exists only zero vector, then inside the null space there is only the zero vector, so M can only be equal to 0. As a result, I will never be able to find another exact solution because M will always be equal to 0 here. So my all solutions that I find is going to be equal to XC, my original solution. Okay? In the first example that we solved, the null space of the matrix A was composed of only the zero vector. That was why the solution was unique. Okay? In the last example, my null space is one-dimensional. Okay? There exist non-zero vectors inside the null space. That is why, in this case, our solution really is not unique. Okay? Solution is not unique. And you see that this is only related to the null space, whether there exist non-zero vectors inside the null space or not. If not, if our null space is only composed of zero vector, then the solution is unique. If there exist non-zero vectors inside the null space, then the solution can never be unique. And actually here, in this null space, in this one-dimensional null space, this is a line in R2. Okay? This is a line which is looking like this. Any vector on this line is a vector inside null space of A for this example. Okay? That means that there are infinitely many vectors inside the null space, infinitely many non-zero vectors, which means that if my null space is just given like this, then I will have infinitely many solutions, infinitely many exact solutions. When I have one exact solution, then I would have infinitely many solutions. Okay? So we have seen the existence and the uniqueness properties of the equation AX equals to B. Now I'm ready actually to write our answers. So let us write the answers. So the answer of the first question, let me write answers here. The answer for the first question, does there exist an exact solution? The answer is there exists an exact solution if and only if IFF B is in range space of A. Okay? Existence is related to the range space of A. And the answer to the second question, when we have an exact solution, the solution is unique. Is unique if and only if. There is uniqueness if the null space is composed of only the zero vector. Null space of A is composed of zero vector. Of course, you need to understand here, this is 0V, zero of the linear space, not the zero scalar. Okay? And, or you can write, instead of this, if and only if dimension of null space of A is equal to 0. Okay? These two are equivalent conditions. Can the null space be an empty set? So can I write here, these are the answers of these questions. So just a side question. This is not related to AX equals to B, but the question is, can the null space of A be an empty set? This one, or just this one? No elements in it. So in the earlier parts of the course, you have probably seen that null space of A is a subspace. Okay? A subspace can never be an empty set. It should always contain the zero vector. And this subspace containing only the zero vector is the smallest subspace that you can have. Here you can give another answer. Does this equation, is there a case when this equation, this is the null space equation, is there a case when this equation has no solution? Obviously the answer should be no, because when x is equal to 0, ax should be equal to 0. So x equals to 0 is always inside the null space. So the null space can never be an empty set, or you can never show it with a phi, or you can never show it with an empty set notation like this. The null space always contains the zero vector. It's a subspace of the domain. Okay? So this actually gives you the initial theory, and we're going to actually continue as follows. So I will just give a brief summary of what we are going to do. So suppose that we have an equation Ax equals to B, and suppose that we don't have an exact solution. B is not in range space of A. Okay? In general, as engineers, we really do not stop at this point. So this equation does not have an exact solution. Okay, so I give up. I really do not want to find anything. As an engineer, we really do not stop at this point when this equation does not have any exact solution. In that case, we would look for some approximate solution. Okay? In this case, we know that there doesn't exist any exact solution, so we always look for an approximate solution. And how do we find that approximate solution? We do this by minimizing an error. And this error, we define it as this norm, Ax minus B. We find the x value or x vectors which would minimize this type of error. Okay? We show in the next part of the course, I'm going to show that such a solution, minimizing this x, would always exist. Okay? And sometimes it won't be unique, but it will always exist. And we are going to learn how we can find such a solution. If I find a solution like this, if I find an x which minimizes this cost, that is called the argument of the minimization, and I will call it x set. That x set is going to be called as the minimum error solution of this equation. The equation doesn't have an exact solution, but it might have a minimum error solution. And this arg is the argument of the minimization, the x vector which obtains this minimum value. Okay? It's called as the argument of the minimization of this error. It's called x set, and it's going to be called the minimum error solution. And we will always be able to find it by using some ideas from the projection theorem. And sometimes this minimum error solution will be unique. In that case, we might stop. So we have a unique minimum error solution. Depending on the null space of A, minimum error solution might be unique, or there might be infinitely many minimum error solutions. In that case, when we have a non-unique minimum error solutions, we are going to try to find the minimum norm solution. When we don't have uniqueness among the solutions, among the minimum error solutions, we are going to try to select a very, very specific one. And we're going to try to select the minimum error solution with minimum norm. Okay? And the argument of this minimization is going to be called x set 1. And this is going to be called the unique minimum error, minimum norm solution. Among all minimum error solutions, we're going to try to select, in the infinitely many solutions, we're going to try to select the one with minimum norm. And that is going to be a unique solution, actually. And we're going to be calling it the minimum error, minimum norm solution. And it is going to be unique. And that is going to finalize this topic. In this lecture, these parts really are not important. I'm going to be repeating these parts in the coming lectures. So if you didn't understand something or anything here, it really doesn't matter. We are going to be going over them one by one. So that is going to be all for this first lecture. I would like to thank you for watching. Bye-bye.